So today we are in class 22. The topics are solution of heat problems with Laplace transformation, heat conduction in semi-bounded rod. So in previous class we talked about application of Laplace transformation for the solution of wave problem. Now today is the heat. Okay, today we consider heat problem. Before this, I want to add some more formulas for Laplace transformation. If you remember previous class, I give you about 36 formulas for Laplace transformation, but we need today some additional formulas. These formulas are for Laplace transformation. So we can see on the left side is original function I cannot enlarge it. How is enlarged? Okay. So if your function is like this, 1 over root of t exponential minus a square over 4t, a is some constant, then its Laplace transformation is this function, exponential minus a root of s over s. Okay. Another is if your function is like this, a over 2 root of pi t cubed exponential minus a square over 4t, and then its transformation is exponential minus a root of s. So if you have an error function complementary of a over 2 root of t, then its Laplace transformation is this function, exponential minus a root of s over s. And if your function like this, and its transformation is this function, and so on. This is additional, some formulas, additional for previous. So why we need this formula? Actually, we will use this table to find inverse, right? Let's say you have a Fs. If you know Laplace transformation, you have image signal, then how to find original signal Ft, right? This is, we call it inverse transformation, Laplace inverse. Laplace inverse. Laplace inverse. Okay, so when you have function like this, then its inverse will be this. For example, let's say your function is exponential. If your Fs, let's say your Fs is exponential minus x root of s over s. So then what is the pre-image, original, right? You use this formula, right? Because it's look like this, and you see your a is x, right? Then what will be your function, original function ft will be what? Error function, complementary, x over, because a is x, right? Root 2 root of t. So we take transformation as function of t, not x, right? So this is how to find using table original signal if you know image signal. Okay. So we will use this table, this additional table for today. And also let me remind some formulas which we used previously. So if you have a function uxt, let's say it is a heat at point t, at point x, at time t, okay? Then by u capital xs, we denote Laplace transformation of u with respect to variable t. Then result will be function of x and s. By definition, it is the integral from 0 to infinity uxt exponential minus st dt. This is Laplace transformation of uxt, right? So we denote by u capital. So then let me remind something regarding relation between Laplace transformation and derivative, right? For example, if you have Laplace transformation of ut, So what is the Laplace transformation of ut? So Laplace transformation is killing this derivative, and the result will be what? Result will be s times u xs minus ux0. Remember this formula? We have this formula. We will use this formula for the solution of heat problem, because in heat problem we have only one derivative. And of course, the Laplace transformation is nothing to do with derivative with respect to x, because transformation is with respect to t. If you have function uxx, for example, uxx, then what is this transformation? It is u capital XX. So Laplace transformation is not killing this xx, because transformation is with respect to t. Now, taking into consideration these two formulas, let's consider the following problem. Let me bring this problem, copy and paste. Okay, copy, and let me bring here. Control V, right? Copy. So we have this problem. So this is heat conduction problem in a rod. Let's say exercise number 1. So length of rod is equal 1. Rod of length is equal 1. So heat conductivity coefficient is equal 1. So it is non-homogeneous. So how you will solve this actually? We learned to solve it we have initial condition 0, right? We have here 0 U0 temperature, right? It's about like this. You have a rod, length is equal 1. All the time we keep 0 on left hand. We keep 0 on the left hand, 0. On the right hand, we keep U0. What will be next? Initially, it is 0. Initially, it is 0. At initial time, it was heated by 0. Then what will happen is U0 heat, which is if it is different, if U0 is different from 0, if U0 is different from 0, then heat will start to move this direction, right? And it is about heating of the rod from the right-hand end. We can call this problem like this. Okay, in mathematical language, we call it heat conduction problem with non-homogeneous boundary condition. Right? When boundary condition non-homogeneous, then old method, okay, method 1, let's say method 1. Method 1, what you do is do step 1. So you will make boundary conditions 0, right? Then step 2, find V. So find V and U. So we already done this. We know this how to do. Okay, but we will solve this problem or try to solve this problem by method 2, new method, right? Method 2 is Laplace transformation method. Okay, so we will transform our problem, means we have to transform equation, we need to transform boundary condition, we need to transform initial condition we use in transformation of equation, because equation requires initial condition. You see what is the initial condition? Initial condition is here. When you transform derivative with respect to t, you needed to use initial condition, right? Okay, let's say equation first. Let's transform equation. Our equation is ut is equal uxx, right? So then what will be transformation of this equation? In Laplace transformation, ut is changing into be as u minus ux0. ux0, right? Is equal uxx will be u capital XX. Okay? So ux0, then your equation will be s times u capital is equal uxx. And you can rewrite this equation like this: uxx minus s times u is equal 0. This is exactly equation 111 in lecture number 1. Okay, 111. And solution of 111 depends on this constant, right? We have minus s is positive. Because s is positive, right, then solution u xs has a form is equal a times cosine hyperbolic, or you can use also exponential form, but we will use in this case hyperbolic form. So what will be this? Cosine hyperbolic root of s x plus b times sine hyperbolic root of s x, right? Root of lambda, remember root of lambda minus lambda, root of minus lambda, lambda is minus s, so it will be root of s. To find a and b, we will use boundary conditions. We have two boundary conditions. Okay, two boundary conditions. Let me see. First boundary condition: u0t is equal to 0. Okay, u0t is equal to 0. u0t is equal to 0. So I must transform because my function is u capital. I needed to transform to u capital. Transformation of this equation in Laplace transformation will be u is transforming to u capital, bracket is bracket, 0 it's x is not changing, x is 0, t is changing to s, equal, transformation of 0 is 0. You see, we have this one. Okay, if you use this one, if you substitute here x equals 0, what will happen? u 0s, now I use u 0s, I use this one. So it is a times cosine hyperbolic 0 plus b times sine hyperbolic 0, right? Because x is 0, it's equal a. Because cosine hyperbolic 0 is 1, sine hyperbolic 0 is 0. So you can compare with this, you will find that a must be equal 0. A must be equal 0. So if a is 0, then what will happen with my u, this u? u xs is equal b times sine hyperbolic root of sx. So a already is 0. Now to find b, we will use another boundary condition. Second boundary condition was u. I see u1. What was the u1t is equal u0. Okay, u1t is equal u0. So what is the transformation of this equation? U is transforming to u capital. 1 is changing, no changes, because 1 is x. X is no changes in transformation. T is changing to s. u0, what is transformation of u0? It is u0 over s, right? This is transformation of u0. Because u0 constant, transformation of 1 is 1 over s. Now let me just write the same thing for this. u1s then equal b times sine hyperbolic root of s. X is 1, right? So this must be equal u0 over s. Now I can find b. What is the b? From this we can find b. b is equal u0 times sine hyperbolic root of s over s. This is a b. Clear? This is b. Now I can substitute b here and find u capital. So u capital xs is equal b, which is u0. So let me write 1 over s. So then I will write two hyperbolic functions times sine hyperbolic root of sx, this one, right? Then this one. Oh, this is on denominator, sorry. It's going to be in denominator, right? This is going to denominator sine. 1 over s times sine hyperbolic root of s, right? Then this is coming here, sine hyperbolic root of s. Okay? So this is u capital. So we don't know u small u. We don't know u, xt. We want to find the solution, but we know what is the image of the solution, right? For that, we needed to transform back using inverse transformation, right? What is the inverse transformation? We have many formulas. In previous class, I give you 36 formulas. Now today, more formulas. You try to find from the right side something like this. 1 over s times sine hyperbolic over sine hyperbolic, and then you will look at left side and find the u. If you see these formulas and formulas in previous class, you will not find something like this. Sine hyperbolic over sine hyperbolic. I will show you. There is nothing like this. You see Fs, F capital S, there is nothing like sine hyperbolic, sine hyperbolic. Okay? So it means this formula is not enough. Also, we cannot find any formula which is suitable from the previous 36. So what we will do, we will try to bring this u capital in some of formulas which we can apply. So we will make some changes in this u capital. Let me write u capital. To make changes, let me remind you what is a sine hyperbolic. Sine hyperbolic is exponential, right? Exponenta. So let me rewrite this like this. uxs is equal u0. U0 is constant, it plays no role. 1 over s is important because s is in denominator, because we are transforming back s to t, right? We're transforming back s to t. That's why this s is important. Now, what is this sine hyperbolic? Sine hyperbolic is exponenta root of sx minus exponenta minus root of sx. This is numerator over 2. I will not write over 2 because denominator also has over 2. So that's why denominator I will write like this. Exponenta root of s minus exponenta minus root of s. Over 2 I am not writing because over 2 we have in numerator and denominator, which will cancel. So now I look at this and say, oh, I have something like this. I have s in denominator and I have exponential root of s. And if I look again, still I cannot find something like this. But you see this formula which we have seen, it is exponential root of s over s. So I must make changes in my formula, and I will try to write it like this, exponential root of s over s. Because I have actually here exponential root of as, so because I know what is a, here a in first is a is minus x, here is plus x, here is 1, here is minus 1, so I have as, maybe hopefully we can bring it, right? So first of all, what I don't like is denominator. So let me take out this exponential outside. Let me write this like this, u0, I will not touch u0, times 1 over s, I don't touch this. So let me don't touch numerator, exponential root of sx minus exponential minus root of sx. So I want to take out this exponential root of s outside of bracket. Inside this bracket will be 1 minus exponential minus 2 root of s. What now we can do? We can lift this exponential up. This exponential you can lift up. When you lift up, it will be exponential minus root of s, right? Minus root of s. It's equal u0 1 over s. So exponential minus root of s times exponential root of sx minus exponential minus root of sx. Now this exponential is going to be upstairs. And I have here 1 minus exponential minus 2 root of s. Then I can bring this exponent inside of this bracket, and I can write like this: u0, 1 over s. Exponent, if I bring this, will be root of s. Root of s, can I write like this? First one, minus x, no, 1 minus x, 1 minus x, root of s. So this multiplication of these two exponents will be minus 1 minus x root of s minus exponent. When I bring this will be minus 1 plus x root of s. Okay? Then exponential minus 2 root of s. So still denominator, this is 1 minus, this is not good. 1 minus, this is not good. So what can we do with this? Somebody requesting to join. What's the problem? Nobody requesting. Okay. Okay. Now requesting. Okay. Anybody requesting? Okay. Now we have to do something with this 1 minus exponent. What we can do with this 1 minus exponent? Okay. Just let me remind you. Just let's use different color. Let's say just a reminder. Maclaurin series. Maclaurin series. I want to remind you Maclaurin series, right? So if you have a function fx, remember fx, what was the Maclaurin series? Maclaurin series is sum k from 0 to infinity, fk, k's derivative at 0 over k factorial x power k, right? X power k. Okay? Let me just use fx is equal, if you have fx is equal 1 over 1 minus x. If you use this, if you write for this Maclaurin series, will be like this: sum k from 0 to infinity, x power k, x power k, x power k, x power k. See Maclaurin series of these functions like this. I'm not going to do this check Maclaurin series, but you can check. Okay, you can check. It's x power k, not just x power k. Okay. For that, you needed to find the derivatives of this function. You can just find the derivatives. It will be k factorial. When k equals 0, k factorial will cancel. This is Maclaurin series of function 1 over 1 minus x. Okay. Then I will use this. I want to use this formula, this Maclaurin series, for the function. Now I will replace x with this. You see, if I use this Maclaurin series for this 1 over 1 minus exponential minus 2 root of s. This one. You see, denominator. This one. If I use this one for this denominator, it's 1 over 1 minus exponent, right? Then what will be? This x is actually this exponent, right? This is equal k from 0 to infinity. X is exponential minus 2k root of s. Right? It's a very beautiful formula using Maclaurin series. This 1 over 1 minus exponential minus 2 root of s, we can write like this: sum from k from infinity 0 infinity exponential minus 2k root of s. Just using this Maclaurin series. Now I will replace. Now, what is my u? Let me continue. My ux s is equal. We have u0. Somebody asking to join or not? Okay, down. u0, we have u0, we have 1 over s, right? 1 over s. So what else we have? Let's see what we have. So we have this stuff. So we have exponenta minus 1 minus x root of s minus exponenta minus 1 plus x root of s. Then we have 1 over 1 minus exponenta minus 2 root of s. Then we replace this one with this series, Maclaurin series, right? If we replace, I just copy from above. Now I will replace with Maclaurin series u0 times 1 over s. So this one exponenta minus 1 minus x root of s minus exponenta minus 1 plus x root of s. Then this I will replace with Maclaurin series k equals 0 to infinity exponenta minus 2k root of s, right? Then I can bring, still we don't have any formula above to get inverse. So, but I'm trying to bring. So equal, now I will bring this, this times this series and this times this series. I can write two series, or I can write one. Let me write like this, u0. Then after u0, I will write series. Everything, rest things I will bring inside the series. So it will be, what will be? Exponenta times exponenta. Exponenta times exponenta, then this exponenta will be added, right? So first will be exponenta. So minus 1 plus 2k minus x root of s. Clear? This times this. Minus, both has minus 1 plus 2k minus x root of s. Over s, I have this over s. Then I have minus. Now I will multiply this exponenta. This will be exponenta minus 2k plus 1 plus x root of s over s. So now you see, I can use this formula. You see, it's what is this? U0 is a constant, summation is a summation. So I needed to inverse back s. Wherever I see s, I have to get inverse. So I have here, what is this? This function is exponenta minus a times root of s over s. The same, e power exponenta minus a, now a is different, root of s over s, you see? It's exactly like this. It's exponenta minus a root of s over s. And inverse is this one, error function, complementary a over 2 root of t. A is this a. Whatever a is, I must write here. So, okay, now let's do inverse. So what will be inverse? Inverse is actually my function uxt. Now, inverse of this, u0 is u0, summation is summation, right? So what about first? This will be error function complementary. What is it? A is 1 plus 2k plus x minus x. Sorry. Over 2 root of t. This one is error function complementary, 2k plus 1 plus x over 2 root of t. Done. This is a solution. So we find the solution in terms of series with error functions. So this is usage of Laplace transformation in the solution of this problem. So if you look at this problem, and if I ask you which method is easy, you will say, of course, method 1. Because you know this, you can make boundary conditions 0 easily. For this, you need to use appropriate transformation, right? V is equal U minus x over x u0 x. This will be transformation. If you use this transformation, it will make your boundary condition 0. Then you will find the problem for V. Problem for V will be with boundary, 0 boundary conditions. Then you can go to step 2 and find the V. Then you will find the U from this equation, right? But if you use Laplace transformation, it seems it's complicated, but you will get, in any case, you will get this solution. But the question is, why need we method 2 if it looks like complicated, right? So to explain this, let me bring next problem. Okay, let me bring next problem. So we have a group of problems. Copy. So problems 11, 12, 13, 14. Is all these problems, I try to enlarge, but I don't know, something wrong with. Cannot catch this. Huh. Okay, cannot. Okay, I think we can read it. In problems 114, use Laplace transform to solve sheet equation subject to the given condition. Okay, if you look at this, you can see x is in this problem, x is more than 0. What does it mean, x more than 0? It's from 0 to infinity. So we are talking about semi-bounded rod. Semi-bounded rod. It is semi-bounded rod. And of course, L is equal to infinity, and you cannot find eigenvalues and eigenfunctions. So method 1 requires eigenvalues and eigenfunctions, right? Now you cannot do this because it is semi-bounded rod. You have no choice. You have to use method 2. Method 1 is not working, right? Method 1 not applicable. Not applicable. So you have to use Laplace transformation. Let's say equation, this one equation. So we have boundary condition here, 1, because only x equals 0 boundary. At infinity, we have another condition, which is condition at infinity, and initial condition. Let me write this 11 as usual we write. So number 11. Equation, what is the equation? Equation is ut is equal uxx. So we have boundary conditions. We have 2 boundary conditions actually. U0t is equal u0, and limit when x goes to infinity, boundary condition at infinity, uxt is equal u1. Okay? And initial condition as follows: ux11 ux0 is equal u1. ux0 is equal u1. Okay. Now let me do transformation of this problem here. Write me this in a transformation form. So I will transform this using Laplace transformation. So what will happen with the equation? Equation is uxx is uxx, right? What is ut? Ut is su minus ux0, right? So su I can shift here, minus su is equal minus u1. So this will be transformation. I use equation and initial condition, right? So uxx minus su is equal minus u1. Okay, this is now boundary condition. What is the boundary condition? U0t is equal u0 will be u 0 s is equal u0 over s. Okay. The second is limit when x goes to infinity. So u xs is equal u1 over s. So this is transformation of this boundary condition. So this is a problem for u. This is a problem for u capital. Problem for u capital, for image, right? This problem we studied actually in lecture number 1. We know the solution of equation, right? From lecture number 1. From lecture number 1, it follows that solution of equation u is equal up, which is a particular solution, and plus uc, which is complementary solution, right? Particular solution and complementary solution. So particular solution, up, if you find by formula in lecture 1, it will be equal minus, not minus, it will be equal u1 over s. u1 over s will be solution. Let's check. So if u is u1 over s, so u1 over s, if your up, you see up is equal, I said up is equal u1 over s. What is up? It is a constant. It is a constant with respect to x, right? Then derivative, it's equal 0. Derivative from up is equal 0. Then when you substitute up here, s will cancel with s. The result will be minus u1. So up is a particular solution. We verified also. It's done. So up is this. What about uc? uc is equal a times exponenta root of sx plus b times exponenta minus root of s x. This is a UC complementary solution, complementary solution of the equation 1, 1 in lecture number 1. So equation 1, 1. Equation 1, 1. If you see first equation, solution is like this. No, 1, 1. It is 1, 8, sorry. So then u is equal, uxs is equal up, I can write up, which is 1 over s, plus a times exponential root of sx, plus b times exponential minus root of sx. Now we will use boundary conditions to find a and b. Okay, let's start with b, because b we will find from second. No, first a, okay, from second. Let's use this one. Limit u capital xs is equal u1 over s, okay? Let me write. Limit, when x goes to infinity, u capital xs, this is u capital, right? I need to write x goes to infinity. So what will be limit of u1 over s when x goes to infinity? It is u1 over s, because u1 over s is a constant with respect to x, and its limit also the same constant, right? So plus limit, when x goes to infinity, a times exponential root of sx, plus limit b times exponential minus root of x, root of s x, when x goes to infinity, right? This one is 0. Why? Because exponential minus x, when x goes to infinity, exponential will be 0. What will be happen with this? This is going to infinity. Exponential infinity is infinity. What must be result according to boundary conditions? This must be equal to u1 over s. Look at boundary condition. It must be u1 over s. When it will be u1 over s? This last term is 0. First term is u1 over s, then second term must be 0. So then what we conclude? A must be 0. If A is not 0, then we have catastrophe, right? This is going to infinity. A must be 0. No way. A is 0. So if A is 0, then my uxs without A, will be just b times exponential minus root of sx, right? If a is 0. So plus u1 over s, okay. Plus u1 over s. Plus u1 over s. So this is a b a is equal 0, then u is this. Now I will use second boundary condition. What is the second boundary condition? u0s is equal u0 over s. u0s, u0s is equal b, right? Because when x equals 0, exponential b plus u1 over s must be equal u0 over s. So from this I can find b. What is the b? b is equal u0 minus u1 over s. Now I can substitute b here and find u. u capital xs is equal b. b is u0 minus u1 times exponential minus x times root of s. I just replace root of s and x. So over s, this s, right? Plus u1 over s. Now I can find inverse of this. So what will be inverse? Inverse, if I do inverse transformation, I can find uxt. So this is a constant. u0 minus u1 is a constant. Now what is this? Again, use the same formula. You see, a is equal x. This is error function, complementary x over 2 root of t. Right, first one. A second one is just u1. So this is the solution of the problem. This is the solution of problem 11. Any questions? Okay, if no questions, let's go and take one more. Let's take number 12. Equation is the same. ut is equal uxx. Now let's say what is the boundary conditions. Number 12, we are looking for this, right? u0t is equal u0. Limit of this is equal u1. Now boundary conditions, u0t is equal u0. Limit when x goes to infinity, uxt over x is equal u1. Let me check again. Yeah, uxt over x. So then ux0, initial condition ux0 is equal u1x. So initial condition is ux0 is equal u1 times x. So this is the original problem, right? Let me now write what will be transformation of this problem, right? What will be transformation, Laplace transformation? What will happen with the equation? uxx, I write first to the right side, first uxx, when you transform this ut, will be what? Will be minus s times u. On the right side, I will have this one, minus u1 times x. So this is the equation. First boundary condition, if I transform, will be the same. u0s is equal u0 over 2. And limit, when x goes to infinity, uxt over x is equal u1 over s. Transformation of u1 is u1 over s. So this is a problem for u capital. This is ordinary differential equation. We can use lecture number 1 and solve this as we did in previous exercise. So solution we need a u is equal up plus us uc. So what will be up for this? If you find up for this will be u1 times x over s. So why it is a solution of this equation? It's particular solution. Why it is a solution? When you take derivative from this, up prime. So what will be derivative? It will be equal u1 over s. Derivative of x is 1. But second derivative will be 0, right? Second derivative will be 0. That's why this term will be 0. This term vanishing, UXX vanishing for UP. Then you have minus SU. If you substitute S here, then S will cancel, will be minus U1X. So it is a solution, right? We have particular solution of equation, UP. This is UP. Now, what is a UC? Again, I will use the same form. UC is equal A times exponential root of Sx plus B times exponential minus root of Sx. Question number 1. Also, right? Then I will substitute here and write U. What is a UXS? UXS is equal UP, which is a U1X over P plus A times exponential root of Sx plus B times exponential minus root of Sx. Then to find A and B, we will use boundary conditions. We have two boundary conditions. Let's start from second one. So what was the second? Second was this one. Limit when x goes to infinity, UXS over x, right? So you have to divide to x. If you divide, it will be U1, oh, this is not P, this is S. This will be just U1 over S because x will cancel with this x. Limit is constant, plus limit when x goes to infinity exponential A times exponential root of Sx over x plus B times limit x goes to infinity exponential minus root of Sx over x. So you see, surely this will be 0. This limit is equal to 0. I'm not going to repeat the limits. If you calculate this limit using L'Hopital rule, because why I say L'Hopital rule? Because it is 0 over infinity. You see, if you substitute infinity, denominator is infinity. This is 0, 0 over 0. So what about this? This will be, if you use L'Hopital rule, you can prove this is equal to infinity. So then A must be 0. Because total, it must be equal to U1 over S. You see, U1 over S. Then we find that A must be 0. No way. If A is 0, then my function UXS, U capital XS, is equal B times exponential minus root of Sx plus U1 X over S, right? This is our U capital. Okay. Now we can use second boundary condition, which is a U0S is equals U0 over S. This is not 2, this is S. Okay. U0 over S. So it is B exponential 0, 1 plus U1X over S equal U0 over S. So from this you can find, X equals 0, sorry, X equals 0. So from this you can find that B is equal U0 over S, right? Because this is vanishing, U0, U1 times it. Okay, B is equal U0 over S, then what will be U capital is equal U0 over S exponential minus root of Sx plus U1 times X over S. Now, we can find inverse of this is UXT, right? UXT is equal. So again, the same formula, U0, error function, complementary, X over 2 root of T, right? What about this? Only 1 over S, because X is a constant with respect to transformation. U1 is constant, right? So this will be plus U1 times x. So this will be solution of problem 12. Okay, and I want you just follow up with 13 and 14 in the same way. So importance of this problem is these problems you have to use Laplace transformation. You have no way. You cannot solve these problems using method one, eigenvalue, eigenfunctions, because you cannot find eigenvalues because L is equal to infinity. Okay, any questions? So if no questions, so that will be end for this class. Let me stop. So before we go to attending, let me stop recording.